Hi, I'm Ben-Yaakov. This presentation is entitled Power Supply Rejection Ratio of LDOs and Intuitive Analysis. What is an LDO? Basically, we're talking about an amplifier, a DC amplifier. It has an input, which is the V reference, and then the output. And there could be a divider here for feedback to adjusting the output as a function of the input, which is the reference. The difference between an amplifier and an LDO is that usually the reference is inside, and then the pass element, a transistor, is selected such that it could carry a current which is required at the output. LDOs could be for a few milliamps up to a few amps. So this element now is passing the current to the output from the input. Now the pass element could be a BJT or a Mosfet. In the case of a BJT, we can have it as an NPN or PNP. Here is the input side and here is the output side. In a Mosfet, we can have a N-channel or a PMOS or P-channel Mosfet. In this case, the source will be on the input side and the drain will be on the output side. Now, if the pass element is an N-channel, then the gate has to be more positive than the source. This would mean that the gate voltage has to be higher than the output. This would require that the input voltage will be higher than the output voltage if indeed the gate is derived from the input voltage. This can be accomplished actually two ways. One way is to have two inputs, one a power input going to the drain and then to the output, and then a control input which will be higher than the Vin to supply the voltage to the gate, which has to be higher than the source. So by this we can overcome the problem that I've described. Another way to go would be to put a charge pump that will be fed from the input and generate a voltage which is higher than the input in order to drive the gate. Both of these approaches are actually used in commercial products. If, however, the transistor is a PMOS, a P-channel MOSFET, then the gate needs to be at a lower voltage than the source. This would mean that if we have an input voltage, we can derive from it the gate voltage, which is lower than the input voltage, which is okay. So by this, we can actually accomplish a situation in which with a single input, we can drive the unit, and also we can achieve a low input to output voltage, that is, the difference is small. Let's have a look at it also from the point of view of the NPN or the BJT transistor. In this case, the base has to be higher at a higher voltage than the emitter, which means that we need an input voltage which is higher than the output by at least 0.6. In practice, it'll be like 1 volt. On the other hand, if you use a Pnp transistor, then the base has to be at a lower voltage than the emitter, which is the input. So therefore, in this case, we have no problem. And again, we'll be able to get a input to output voltage difference, which is small. This will be here like 0.6. In practice, it'll be probably 1 to 1.5 volt, while here in this configuration, we can get a much lower dropout voltage. So this is the notion of dropout. That is the difference between input and output. Low dropout LDO, meaning that you can operate the unit when Vin is rather close to Vout. The dropout voltage is small. However, one has to take into account that the losses and efficiency really are independent on the question whether the type of the LDO is low dropout or regular LDO, because the efficiency is always V out over V in, very close to it. So no matter what type of LDO you are using, the efficiency is the same, except the fact that if you use a low dropout LDO, you can use it with an input voltage which is very close to the output voltage. However, in regular operation, very seldom you have a situation in which the input is very close to the output. Usually there is some range to it. So as far as efficiency goes, this doesn't make any big difference. Let's turn now to the issue of power supply rejection ratio, which is the subject matter of this presentation. What we mean by that is the penetration of noise or ripple from the input into the output. And we define power supply rejection or ripple rejection or power supply rejection ratio as the ratio. Sometimes it's V in over V out. This is going to be a large number because V out is going to be obviously smaller than V in, or sometimes actually reverse. And then you can have it in dB, 20 log this value. Sometimes there is a minus to it, 1 over. So in general, we are talking about the ratio between V in and V out, one way or the other. And the actual range that we can find in commercial units is somewhere between, say, 90 to 40 dB in the operational range, which is quite a bit of a range. Some are better, some are worse. The larger the number, the better it is. This would mean that the V out is much smaller than V in. This is in dB, of course, so we're talking about 10,000 and more. For the analysis, I'm going to use a simple model of the path element, being a BJT or a Mosfet, and it is based on a dependent source, GM times VB in the case of the BJT transistor. Then we have the HIE or RPi, sometimes it's called the input resistance, and then we have the output resistance. The model for the Mosfet is pretty much the same, except that HIE is very large, so we can assume it's open circuit. But again, we have a GM times the voltage here, and then R out. So basically, these are the same model. Of course, the parameters, the values could be different. So now I'm going to plug in the path element to replace it with the model. So we can see here that for the normal configuration, say this will be like a BJT. Here's the emitter, here's the collector, and here's the base. We have this situation here. This is the output section. Normally we're going to put in output capacitor for reasons that we'll talk about later on, and reducing actually the noise, the ripple here. And this represents the load. R sub L is the load that we have here. Now we're talking about, of course, DC and AC, which we are interested in. This is the error amplifier, and this is the divider. In the reversed mode, they say this is a MOSFET now. This is the source, this is the drain, this is VGS, okay? So we are feeding the output of the error amplifier into the gate, and then the rest of the circuit is pretty much the same. Now let me just point out that in the analysis I'm going to do, I'm talking about the injection through this path. There's another path which is through here, through the control, through here, which I'm not talking about. Usually it's much smaller than the major path that I've shown here. So this is not taken into account now. So let's see what's the difference between the normal or the reverse mode of the path element. In the normal mode, say this is now a transistor, BJT transistor, feeding the signal to the base in reference to the emitter, which is at the output, okay? So this is a current source. So this is like for a disturbance, it's an open circuit, and the injection is actually through here. On the other hand, if we are working with the reverse mode, so this is now a PMOS, the sensitive portion here, terminals are between gate and source, and as we can see here, both the output of the amplifier will affect this voltage and the input disturbance will affect this voltage. So therefore, there is quite a bit of a disturbance coming through here, through the fact that we are affecting the gate to source voltage, and this dependent current source starts to generate signals here, or current, injecting it to the output, as well as this path, which is like a passive path here. So this is the main difference between these two, and one would expect that the power supply rejection ratio of this configuration of the reverse mode, say PMOS or Pnp transistor, will be worse. But as we'll see, there is more to it, okay? So let's do the analysis first and then come to the conclusions. So here is the model that I'm putting up for the analysis. This is a control model. This is not a circuit diagram, it's a control. We are talking about transfer function, and these are the signals that we see here. And let me go over it and first of all explain what's the meaning of it. So what we have here is the amplifier. We have the summing of the reference plus the feedback. For the small signal, this is 0 because we are not assuming any disturbance here, although it can be analyzed for that, but not in this analysis I'm talking about. And then for the general case, for the reversed case, we have a summing of this signal plus the signal coming from Vin. This is generating a current through GM. This voltage through GM is generating a current, which is then added to the current coming through the resistor. Now, the current through the resistor is a function of the voltage difference, V in minus V out, and the resistance, 1 over the resistance. Here it is. This is V in minus V out, and here is the current. These two currents are passing through the output impedance. This is the output impedance to generate the output voltage. So this is the idea of this model. Let me just sort of explain each part by itself. This part is the output impedance. Here, this summing here, the addition of the voltage from the error amplifier and the voltage from Vin is depicted here, or is represented by this summing junction. And then we have this summing junction of this current coming here and this current coming here, and then it is multiplied by Z out to generate V out. And then we have, of course, beta, which is the voltage divider here, to get the scaling of the output as a function of the reference. Now I'm going to do a trick here in order to simplify the analysis, and the trick is that I'm going to, let's see here, to separate this, and instead of having like one input, to have now two inputs. They are the same, but they are now separated. The idea is that if I do that, then I can use superposition. This is a linear circuit. I can do superposition. This simplifies matter quite a bit. That is, rather than handling the whole circuit by itself as a whole, I'm just doing it piece by piece. So the first part will be assuming that this is 0 and I have only injection through here. So here it is. This is the injection through here, and this is the output. Now this is a regular feedback system, okay? So the gain or transfer function between here and here is this times this, GM times Z0, and then the loop gain. This is now the loop gain here, GM, Z out, beta A, 1 plus the loop gain. Very simple. I got it almost immediately. So this is the transfer here. And then I'm coming back to the second part, and this is the injection through the resistor. Well, I can do it here, but this is kind of more complicated because I have two closed loops here. So rather than that, I'm going now back to the original circuit, still separating the two V-ins. So this is now 0, and I'm injecting a signal here. If you inject a signal here, obviously the voltage at the output depends on the impedance that you can see here. the impedance here. Now this is the output impedance of a circuit in closed loop, and we know that the output impedance with feedback is the open loop impedance divided by 1 plus beta A. Now what 1 plus beta A we know. So what is the output impedance without feedback? Well, it is just this impedance here, Z out. So that the output impedance of this circuit with feedback is this Z out, 1 plus GM Z out beta AE, and the actual injection will depend on this voltage divider between R out and the impedance here. Here it is. So this is the injection into here. So this also comes out to be fairly simple. So now we can add these two parts. This is the GM part, this is the R out part. So V in times this function plus this function is V out. So V out over V in is this expression plus this expression when R out F is, as we have said, Z out 1 plus GM Z out beta AE. So these are the full expression for the injection between V in to V out. I'm expressing it here as V out over V in, so it's actually 1 over the conventional power supply rejection definition. So now I'm dividing the operational range in terms of frequency into two ranges, one where the loop gain is larger than 1, and then, of course, when it is smaller than 1. Now, when it is larger than 1, then let's first of all look at what happens with the output impedance. The output impedance is Z out over 1 plus GM Z out beta AE. Then therefore we find that the output impedance is 1 over GM beta AE. AE is very large, it's a large gain error amplifier, and therefore this is very small. And therefore this divider that we have with R out is the resistance of the pass element, which is usually fairly high, it could be in a range of 1 megohm. This drops out. So we are left with this part here. Now we're talking about the loop gain larger than 1, so this one drops. So GM Z out is also dropping out, and lo and behold, we get this expression 1 over beta AE. AE is the gain of the amplifier. So power supply rejection ratio in the operational mode of the amplifier, that is when it's still operational, that there's sufficient feedback, that is below the crossover frequency, is the beta, which could be a function of frequency, and obviously the error amplifier gain, which is a function of frequency. So with the large gain here, or large bandwidth here, we can get very good power supply rejection ratio throughout this path, while the path through the R out of the transistor is actually very small. Now what about the case that the loop gain is smaller than 1? So what happens first of all with this portion here? This portion here, we are losing this gain, so the output impedance is just Z out. This is what we see when we look into the LDO. However, Z out in this range is fairly small because we have an output capacitor, and we are talking about high frequency beyond the crossover frequency of the error amplifier. So therefore, Z out will be much smaller than R out of the transistor, and therefore again this part here actually does make big difference if there is something here, if it is left by itself, and this will be the case in the normal mode. Well, I'll talk about it in a minute. I'm talking now the reverse mode, in which we have this portion here. So in this case, this will be negligibly small, and we can cross it out. So we are left with this part here. Now, loop gain is smaller than 1, so we are left with this. So this is now V out over V in, and power supply rejection ratio will be 1 over this value here. Now obviously, if Z out is small because of the capacitor at high frequency, then the power supply rejection ratio could be fairly high. So let's now compare the two cases, the reverse mode, which we just analyzed, and the normal mode. In the normal mode, we just don't have this path here. It's only left with this. So this is just a residual transfer through the resistor of the element, the path element that we have in the circuit. Now what about the actual transfer functions? The error amplifier, which normally will have a single pole behavior, dominant pole with some crossover frequency, while the impedance is actually the impedance of a network that looks like this. R1 and R2 usually will be much larger than load. This is the load. So this is the circuit. Now, in reality, the capacitor will have a ESL, a equivalent series inductance, and then equivalent series resistance. So the actual behavior of this circuit is at low frequencies is just the output resistance, but then as the frequency goes up, of course the impedance goes down, but then it picks to ESR when the resonance is approached, and then it'll go up a little bit, and then depending on the parasitic of the system. I'm just showing here part of the parasitics. Of course, the transistor itself has capacitances, the circuit itself has capacitances, and these I've not considered, so you'd expect some sort of a behavior here depending on the parasitic. So let's have a look at real commercial units. The most popular one and the oldest one, I think it's the first LDO, is the 7805, or this family, 78, and this 05 meaning that's a 5 volt. You see this is a NPN BJT transistor. This is the pass element, okay? And here we see the ripple rejection or power supply rejection. It's depending on the output voltage. This is not a 5 volt unit, of course. They have a family, some are higher voltages, and we see that's about 80 dB, so it's 10 to the 4th, quite a bit. And this is because we have only the resistance injection, okay? There is no GM here, as we have talked about. And however, it shows here only to 100 kilohertz. It's a very old unit, and at that time, people were not aware of higher frequencies, so it's limited to 100K. Now, what about the output impedance? We see that indeed, when the gain of the error amplifier is high, we see very low output impedance, and then it starts to go up as we would expect. Now, what about the dropout? It's not shown here directly, but we can judge it from this graph. What it shows here is for a 5 volt unit, you increase the input voltage, and then obviously the output will be low at the beginning, and then eventually to stabilize. And you see that it stabilizes to 5 volt when the voltage at the input is about, say, 6.5. So it's a 1.5 volt dropout for this unit, which is typical for NPN transistor type pass elements. Now, what about the case that we have a Pnp transistor? Okay, it is reversed. This is a unit, a more recent unit by Texas Instruments. And here it shows the ripple rejection, which is pretty good, 75. Then it goes down, and then there'll be some oscillation here. And again, it shows only to 1 megahertz. Now, the output impedance also shows low value up to, say, a few kilohertz. This will be the portion of the frequency where the gain of the error amplifier is high, and then of course it goes up again. Now, what about the dropout? Okay, here this is something else. We see that it depends on the current you need to pass through it, but say for 400 milliamp, it's only 0.2. That is, you can operate the unit with a 0.2 volt difference between the input and output, and this is because the transistor is reversed. You can pull down this voltage at the base without any problem. You don't need a higher voltage, and therefore you can operate the unit pretty close to zero. And here it is. Now, here is the unit now with an N channel. This is the N channel, and it has two inputs, one for the power and one for the control. Okay, and here's the output with this transistor. So what about the power supply rejection ratio? We have now two types of power supply rejection ratio. We have the power input, V in, and then we have the control input. The control input, it's not that good, but it really doesn't matter that much because the current there is very low, and we can filter out the signal as it gets into the unit. So by having an added filter at the input, we can actually attenuate it at the input side, and therefore the injection to the output will be very small. But this is the main power, and we see here the function of frequency, and you see that at the beginning it is a negative number, so it's sort of flipped over. It's 65 dB or so, and then it goes down again. The bandwidth is looks like this is 1 kilohertz, so this is 344 kilohertz, the bandwidth, and then it goes down again. So the fact that you have an N channel does not significantly improve the power supply rejection ratio, and as I have said, the reason is that it is affected by the amplifier. So by having a very good amplifier, you can get good result independent actually on the configuration of the pass element. So now this is the classical low dropout P-channel LDO. This is one example, of course. Here's the pass element. This is now the source, the drain, and the gate. And here we see that it's not too bad. It's comparable to what we have seen before with the normal mode. And it is like 70. This is because of the measurements, I guess. That's not real. And then we see the drop as the amplifier, of course, is losing the gain. And then we see some peaking, part of it due to this capacitor resonance effect. So here we have now the dropout voltage. I guess this is just an error. This is millivolt. That's not volt. That's not 150 volts. So this is the millivolt. And here's the output current. And we can see that for, say, mid-range here, we're talking about 100 millivolt, which is very nice. Again, if you need it, you have to have a situation that your input is always 100 millivolt higher than the output. If this is the case, you can obviously use, you don't need a regulator if it's fixed. Well, sometimes it may drop, like it'll be higher, and then it may drop to close to the VL, then maybe this would be a good reason to use a low dropout unit. And finally, this unit here, which I've just looked up, and here we have a constant current source, so that by putting a resistor you can adjust the reference voltage, so it's a adjustable reference here. It is a BJT transistor, Pnp, so it's the worst case presumably, but if we look at the performance, it's really very impressive. You see that the power supply rejection ratio is above 100 dB, so it's depending on the setup, it could reach much higher than that. At very low frequency, it's 80, 85 dB, and then it goes up to very high value, and then it drops, but again, this is 80 dB, so this is indeed impressive. Now, what about the dropout? The dropout here is between 200 to 250, depending again on the current. As the current goes up, the dropout of course, increases. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.